There's nothing quite like the smell of freshly planed walnut. But that's not what we're here to talk about today. Today we're going to be talking about binary numbers. Now, the thing about numbers are an abstract idea. You can't have a bucket of 5. There's no physical number 3 out there anywhere. Numbers are just an idea, and the symbols we use to represent the numbers are arbitrarily chosen. We use the Arabic numerals, 0 through 9, and then when we need more than 9, we put in another place. But it hasn't always been this way. The Babylonians had 60 digits before they started over. So imagine being a Babylonian child and having to learn the symbols from 1 through 60. They didn't have a symbol for 0. Now, it's the Babylonians that give us things like 60 minutes in an hour, 60 seconds in a minute. Those are all based on the Babylonian system. That's also why we have degrees. Because if you have an equilateral triangle, each angle is 60 degrees. You can thank the Babylonians for that system. Still makes more sense than radians, though. Now, one of the things that the Babylonians invented that we carried on was the idea of positional number systems. Now, with a positional number system, the important thing to understand is the base. We're used to a base 10 number system, where we have 10 different digits, 0 through 9. But we don't have to have 10 separate digits. As I said before, the Babylonians had 60 of them. So, if you use a different base, you can still represent the same numbers, but you're just representing them in a different way. Now, one of the things about math that a lot of people don't realize, it's a nifty little trick, is that when you're talking about base, imagine the base of your number, in our case 10, and then imagine an exponent. Now, 10 to the first is 10, just like any number to the first is itself. That gives you how many numbers you can represent with that many digits. One digit, we can represent 10 numbers. Let's do 10 to the second, which is 100. We can represent the numbers 0 through 99 with 2 digits. 10 to the third, 1,000. We can represent 0 through 999, or 1,000 numbers, with 3 digits. And this holds true no matter what base you're using. If you're using base 16, otherwise known as hexadecimal, you can represent the numbers 0 through F with 1 digit. F being the digital or decimal equivalent to 15. Now, you may remember in class that I said that anyone that works in computers needs to know their powers of 2. You need to be able to count up to at least 4096. And the powers of 2, 2 to the first, which is 2, 2 to the second, which is 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. You need to know these numbers. Now, if you're going to be a network administrator, you need to know these numbers because you will still use them quite a lot. Plus, whenever you get memory or disk space or things of that nature, you're all going to be dealing with powers of 2. You'll notice how common it is to have 2 gigs of RAM or 16 gigs of RAM. But have you ever heard of anybody that had 15 gigs of RAM? It's really hard to get 15 gigs of RAM because all of the sticks are sold in powers of 2. Alright, if you're a programmer, you also need to know the powers of 2 because you'll be dealing with powers of 2 in your code. The size of an integer will be, for instance, on a DOS system, 16 bits. which can represent any number between 0 and 65,535. If you have a 32-bit integer, it can store to the 32nd power, which I don't actually know off the top of my head. Just like with decimal numbers, each place in a binary number represents a power of 2. So for 2 to the first, which is the first digit, we can represent 2 values, either a 0 or a 1. Second place, we can represent 2 values, which will either be 0 or 2. And the next, we can represent 0 or 4. And so on, all the way up the list. Now, if you want to convert a decimal number to binary, it's relatively easy to do. Let's take a number, and then let's subtract the largest power of 2 that we can from that number. Then we'll put that number in the appropriate place in the binary number. We'll place a 1. Now, we'll take that new number and we'll repeat the process until the new number becomes 0. Converting from binary to decimal, you basically do the reverse. You take the largest digit out of the binary and put that in place. Then you take the next number and then add it to that, and the next, all the way until you get 0. There's a reason why binary numbers are used in computing. Computers are made of digital circuits. Each digital circuit can either represent a high or a low voltage. And we represent those with a 0 or a 1. If we need to represent numbers going down a line, we can do this pretty easily by having more than one circuit. One example of this is the system bus. The system bus is a number of parallel circuits, and one section of it will be the data bus. Now, the size of the data bus determines how large a value you can store. On an 8-bit data bus, for instance the S100 bus used by early microcomputers, you had a maximum width of 8 binary digits. So at any one time you could represent any number between 0 and 255 on the system bus. Later buses expanded this. For instance, PCI uses 32 circuits in its data bus. So it can represent any number between 0 and a little over 4 billion. One place you will see this in your code is bit fields. Now, bit fields are used all over the computer. The CPU has a number of single-bit registers that it uses for setting options. For instance, an interrupt enable option just takes up 1 bit in a register on the CPU. Now, how would you set just that 1 bit and leave the others untouched? Well, the way you do this is you use what's called a bit mask. And a bit mask is just a number that represents the bits that you want to access or the bits that you want to change. Bit mask in C is represented by either a character or an integer or some sort of numerical type, but generally character. By setting a series of characters and having each bit mean a certain thing, you can pack a lot of data into just one small region of memory. One example of this is in networking. In the IP protocol, which is what the internet uses, the header for each packet contains a series of bits that represent different values. The first value is the version, which you can see takes up 4 bits. That's the version of the IP protocol, normally 4 or 6. The next is the header length, which tells you how many 32-bit words are contained in the header. After that, you have the TOS or DSCP section, which gives a router information on how this packet should be handled, if it should take priority or if it's just a bulk packet that can wait. Next is the ECN, which only takes 2 bits. This is used for dealing with congestion. If packets are being slow, if they need to be routed a different way, the ECN is a section that routers can use to notify each other if there are problems. The next 16 bits represent the total length of the packet in bytes, including the header. What we want to look at is the IP address, which is further down the header. Now, the IP address is 32 bits. Now, how does a router tell what is part of the address and what is part of the network? Because it needs to know this to know where to send the packet. The way it tells is you have a network mask. Now, the network mask is simply a binary number with a series of 1s and a series of 0s. The 1s represent the network, and the 0s represent the host. For a small home network, you generally use 255.255.255.0, or this number here, represented in binary. As you can see, all the 1s are all together, and all the 0s are all together. A router can look at this and tell which part is the network and which part is the host, and know how to deal with the packet accordingly. Another place where binary numbers are used extensively is in graphics. Now, with simple black and white bitmaps, each 1 or 0 can represent a white or a black pixel. This was heavily used in the early days when memory was limited. You could represent quite a few pixels in just one integer. These days, most of the time, pixels are represented in color. And there are quite a few different formats for this, but one that is very common is the RGB format. This uses 8 bits of red, 8 bits of green, and 8 bits of blue. Each pixel takes up 24 bits on the screen. In addition, you can have a further 8 bits for transparency if you need to overlay images. Now, how do we use binary numbers in our code? Well, there are several methods. In the C programming language and C++, we can represent the numbers as a series of characters, where each bit in the character takes exactly 1 number. We can do the same with integers, or longs, or long-longs. But the problem with that is that some machines order the bytes differently. So if you have a long-long on an Intel machine and a long-long on an IBM Power machine, they're not represented the same way. This isn't a problem for if you plan on keeping all your code on the same platform. But if you plan on writing code that works on both, you need to be able to deal with this. If you have a series of characters, they'll be represented the same on both platforms. I'll briefly cover the concept of byte order. Now, some values, like integers, take more than 1 byte to store. And on big Indian systems, the most significant byte is stored first, whereas in little Indian systems, the least significant byte is stored first. Now, the big Indian reads from left to right, all the way across, whereas with little Indian is read right to left, but only for the bytes. The individual bytes themselves, the bits in the byte, are still read from left to right. Historically, most processors were big Indian, But Digital Equipment changed that with the PDP-11, which was very popular, and it was a little Indian system. The VAX and the Alpha, the successors, were also Little Indian, although the Alpha could go either way. But the big win for Little Indian architectures was Intel, who chose Little Indian for their 8086 processor, and that has continued on today all the way up to the modern x86-64 processors that are in most PCs today. Now, the larger, more powerful processors, such as the Itanium, the Power, the Sparks, the things that are used in large enterprise applications, generally tend to run either these days, but they ran Big Indian in the past. Do note, though, that while they can run either, they generally only run one at a time. This is determined either at boot time by the bootloader or by a hardware switch on the motherboard. In C++ or C, you can use the bit shift operator. Now, C++ programmers are familiar with this operator as part of input and output, but that's not its original use. Originally, this was the bit shift operator, and it allowed you to move bits to the left or to the right inside a variable. This gives you a very fast way to multiply or divide by 2, but is also very handy for setting bit fields. If you take the value 1, and then you bit shift it 3 places, all of a sudden now you have the value 8. There are also bitwise logical operators. You have bitwise AND and bitwise OR, represented by the single ampersand and the single pipe. These are used for manipulating bit fields and applying bit masks. If you only want to affect the third and fourth values in a bit field, you create this bit mask. And then you can use this bit mask and apply it to a value and get those values out. This is used extensively in the C programming language. On Unix, the open command will open a file, and you can use a series of bitwise variables to set flags on how this file should be opened. If you want the file to be created if it doesn't exist, you enter this value. But this value only contains one single binary bit, and it's in a certain place. By combining it with other values using bitwise OR, we get a combination of values that set each flag individually. C++ gives us some additional tools to work with bitwise values. When you declare a class, you can set certain storage areas that only use a certain number of bits. This can be handy if you need to conserve space. However, this carries a lot of pitfalls that I won't be covering here. C++ also gives you the bitset class. C++ also gives you the vectors of bools. Now, a Boolean vector only uses one bit for each Boolean value, which can save a considerable amount of space. Now bear in mind, when you start dealing with bit values, you are going to run into problems with portability. If you use bit values to read or write to files, you're going to have problems when you move to different operating systems or architectures. So only use these internally to your program. Do not use them in a file format unless you really know what you're doing. TCP/IP gets around this by using Big Indian values for everything. And there are a set of functions that are used explicitly to convert your values to Big or Little Indian. Alright, now that we know how to work with binary numbers, get out there and write some code. Or turn some wood. I don't care.